This video, we're going to talk about uh, exercises from section 2.4 of the APREX Pre-Calculus textbook. It's entitled Graphs and Graphing. We're mostly going to talk about transformations of functions. So let's talk about what the general form of a function looks like with transformations. Like this, where this is called the parent function that everything is based off of. H is going to be the horizontal shift. K is going to be the vertical shift. And A is going to be the vertical stretch or compression factor. Also, A may also cause a reflection across the x-axis if it's negative. Now, there's a possibility here of sometimes there being a coefficient in front of x, like we have in example 4 here. I'm going to show you how to deal with that later. Typically, we don't write that in here, but there are some functions, especially our trigonometric functions, that we're going to have to deal with that are going to look like this. And we're not going to be able to get B to come out of this, and we're going to have to deal with it. We'll talk about those over here when we get to trigonometric functions and how you deal with what's called phase shift, which is going to deal with and you're going to deal with the change in frequency or wavelength. Your period is what we're going to call this, and those are physics words. Period is a math word. It's a periodic function. So before we get started, you need to know your library of functions that we're going to be dealing with. So let me get a picture of a library of functions for you. 1 second. Okay, so here's the library of functions. I just found a PDF of it online. Our first type of function we have is a constant function, y equals b. We've talked about that in our linear equation section. We also have the identity function, y equals x, and that's going to go through 0, 0, 1, 1, negative 1, 1, where x and y are equal to each other. This is the function from which all lines with finite slope are based off of this function. This is all functions with a slope of 0 are based off of this function. Then we have the squaring function, y equals x squared, and that's going to be a parabola with its vertex at 0, 0. 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4, and so on. All quadratic functions in the form of ax squared plus bx plus c are based off of this function. We're going to get to how you do the transformations on this next time when we talk about completing the square. This is the cubic function. Y is equal to x cubed. It's going to go through 0, 0. It's going to have the point 1, 1, the point 2, 8, the point negative 1, negative 1, and the point negative 2, negative 8 as its characteristic points. It's going to have this special point right here that's at 0, 0 called a point of inflection. We're going to talk about that a whole lot in calculus. It's a point where the graph kind of turns, but it doesn't change from increasing to decreasing or decreasing to increasing. It's increasing. Then it kind of levels out for a second and it continues increasing. The concavity of the graph changes here to where the water is spilling off of the graph here. The water would fill up the graph here. If I would look at this like it's two parabolic pieces, that this parabola it's spilling off and this parabola it's filling up. We see that the in the square root function at the vertex is going to change from decreasing to increasing, or if it's opening the other way, increasing to decreasing. We have a square root function. This is the first of the functions that we see where the domain is restricted because we have to have the inside of the square root be greater than or equal to 0. All even roots are going to be based off of this function, and it's going to be increasing, starting at its vertex at 0, 0. The square root of 1 is 1. The square root of 4 is 2. It's a much slower growing function than any of the other functions that we've looked at so far. We have the inverse function of the cubic function is called the cube root function. It's just like the inverse of the squaring function was the square root function. The inverse of the cubic function is called the cube root function. So we have 0, 0. We have 1/8, 1/2 here because I can take the cube root of 1/8. I can take the cube root of 1 as 1. They showed that I would get 2 cube root of 2, but you don't really know what the cube root of 2 is. I would go all the way out to the next perfect cube is going to be 8. The cube root of 8 is going to be 2. So we're going to have to go way out here to 8 to get the next integer value of 2. And the same thing as we go to the left, that I would get -1/8, -1/2, -1, -1, -8, -2. I could also get some points like 1/4, 1/2, -1, I'm sorry, not 1/4, 1/2, 1/27, 1/3, -1/27, -1/3, but that would be really hard to see there. They're there and there, they're smaller fractions. So I think 1/8 is probably the best one for you to try and get there. Now we've got the reciprocal function from which all rational functions are based off of, either the reciprocal function or the squared reciprocal function or some combination of them. This is the first one where we see asymptotes in the graph. So we have a horizontal asymptote and a vertical asymptote here. And we see that the reciprocal of 1 is 1, the reciprocal of -1 is -1. We see other points like the reciprocal of 1/2 is 2, the reciprocal of 2 is 1/2, the reciprocal of -1/2 is -2, the reciprocal of -2 is -1/2. Now, if we want to square this, remember that a negative times a negative is a positive, so we're going to have only quadrants 1 and 2 here, and we're going to have to square all these values. So 1 squared is still going to be 1, -1 squared is now going to be 1 here. And so where we had 1/2 2, we're now going to have 2 squared is 4. So 1/2 4, 2 1/4, and so on. So those points that I gave you here that were characteristic points are going to square the y value here because 1 over x squared is 1 over x squared. Take a look at the domain here, but the domain does not include 0 in either of these graphs because I'm not allowed to divide by 0. The range changes. Here the range was -infinity to 0, union 0 to infinity. Now the range goes from 0 to infinity, and they mismarked this. This should be a open parenthesis for the range here because 0, y equals 0 is a horizontal asymptote there. I'm going to approach it but not get to it. So that's mismarked. That should be an open parenthesis, not a closed parenthesis. Let me see if there's any other mistakes like that. No, everything else is good. That's the only mistake that I see. I'm going to see if I can edit that right now in my copy. So come here and say needs to be, nope, it's not letting me get rid of that bracket there. Okay, just pretend that it's not there. There we go. Now I got it. One more second. Gonna get inside here to edit it. Okay, now we have the absolute value function. Another way that we can look at the absolute value function, it's going to be important for us to know, is that we can look at it as f of x is going to be equal to the square root of x squared. It's not going to let me draw nicely in here in the PDF, so I'm just going to annotate with a zoom, say this is the same thing as f of x is equal to the square root of x squared. That's also equal to the absolute value of x. Careful with that whenever you see an even power inside of an even root like that, watch out for that. That it could come out like this, where it's equal to the input value. If the input was greater than or equal to 0, it's equal to the opposite of the input value when the input was less than 0. And it's going to be this V-shaped function like this that looks like two lines, where this side over here is the line y equals x for x greater than or equal to 0. And this is y equals negative x for x values that are less than 0. It is an even function. Notice that it has y-axis symmetry. We didn't talk about that with any of the other functions, but we'll go back there in just a second to note which ones are even and which ones are odd. Let's do that right now while I'm thinking about it. This is going to be an even function that has y-axis symmetry. This is going to be an odd function that has origin symmetry. This is an odd function that has origin symmetry. This doesn't have any symmetry. This has origin symmetry. This has y-axis symmetry. This has origin symmetry right now, the way that it's written. This has y-axis symmetry the way that it's written right now, because it reflects over the y-axis. So we have lots of functions with lots of different kinds of symmetry the way that they're written right now. Not every descendant or every child of these parents is going to have the same kind of symmetry as the parents. As soon as you start shifting the graphs, you may mess up the symmetry, and it may no longer have that kind of symmetry. Another type of function you're going to deal with in pre-calculus is an exponential function. We're going to usually deal with the base e, but we don't have to. We could be dealing with the base a, but usually it's going to be written as e to the kx, where k is going to be some kind of growth constant. E to the k could be rewritten as the base a, though, and just be written as a to the x. If a is greater than 1 or k is greater than 0, then we're going to get exponential growth like this. If a is between 0 and 1 or k is less than 0, we're going to get exponential decay like this. In both cases, our domain is going to go from negative infinity to infinity. We're going to go all the way to the left and all the way to the right, and our range is going to stay above 0. Our outputs, and it's not going to include 0. There's a horizontal asymptote here at 0 that it approaches but doesn't touch. We get these where something is changing every instant in time, like continuously compounding interest. We also have this type of model with radioactive decay, with growth of populations or cultures like bacteria cultures, populations of animals or people, those sorts of things, especially when you're talking about rabbits that are reproducing. They reproduce at an exponential rate. So we also have other things that we would learn about later in science and math that have to deal with this, such as the time that it takes for a cake to cool when you take it out of the oven, or something along those lines. So the inverse of exponential is going to be logarithmic. We're going to look at the natural log function as the representative parent graph for that, just like we looked at the exponential e to the x up here. We're going to look at log base e to the x down here. Though every y equals log base b of x looks similar, the main difference is going to be in the characteristic points out here, that where this one is going to have y equals 1 at e and y equals -1 at 1 over e. That whatever the base is, if I have this instead as log base a of x, then this would be whatever my base is here. This would be a1, and this would be 1 over a -1. And I could have a squared 2 and 1 over a squared -2. Those would be characteristic points as well. But you're always, no matter what the base is, you're always going to have the point 1, 0 there, because log base anything of 1 is equal to 0. Our domain here is that our x has to be greater than 0. We're not allowed to take the log of a negative number. We're not allowed to take the log of 0. We're going to go all the way to -infinity with our range, all the way to infinity with our range. Now we're going to start to talk about some of the trigonometric functions. We haven't talked a whole lot about them yet. So our sine function, S-I-N-E, gets abbreviated with S-I-N in our calculators. It's a wave that starts, periodic wave that starts at its equilibrium down here, and it goes up, down, down, up. We'll talk more about the unit circle later, but this is going to be related to the y values on the unit circle as well. But this is a wave, and we're going to see that it starts at equilibrium, and it starts going up first, then down, down, and back up. It goes all the way to the left and all the way to the right forever, but it's going to stay between -1 and 1 during its entire set of infinite cycles. It just keeps going on forever. That's what makes trigonometric functions, periodic functions, different from the polynomials and other types of functions that we studied up here. This is part 2 of your pre-calculus, is to study these periodic functions, because they're going to cross the x-axis an infinite amount of times instead of a finite number of times. Cosine function is going to start at maximum displacement, and it's going to go down, down, up, up, and it's going to be related to the x values of the unit circle. Similarly, to the sine function, it's going to have a domain of -infinity to infinity and a range of -1 to 1. Our tangent function is the ratio of sine to cosine, just so you understand why it's doing what it's doing here. This is sine divided by cosine. So the zeros of sine are going to be the zeros of tangent, and the zeros of cosine are going to be the vertical asymptotes of tangent. So we have the zeros of cosine were at odd multiples of pi over 2. And we had the zeros of sine were at the even multiples of pi over 2. So 0, not even multiples, the just the multiples of pi, excuse me. So even multiples of pi over 2 is the same thing as multiples of pi. So we have 0, pi, 2 pi, negative pi, and so on will be zeros of the tangent function. We see that it's going to go to negative infinity and to infinity. It's not going to be stuck between negative 1 and 1 for its range. And its domain is going to be all x values such that x is not equal to a multiple of pi over 2. K is an integer. Right? Now we have some of the reciprocal trig functions. Secant is the reciprocal of cosine. We can almost see the cosine graph getting drawn between these zeros here, that it was at 1, and then it was going down, down, up, up, right? So that's what it was doing here, and the reciprocal of 1 is 1. The reciprocal of 0 was undefined. The reciprocal of -1 is -1. The reciprocal of 0 is undefined, and then it's back up here at 1. So we can kind of see the cosine graph staying between there. We're gonna usually only look at an entire period here that's going to go from negative pi over 2 to 3 pi over 2, but it does keep going, it keeps cycling. And again, we're going to exclude the multiples of pi over 2 of cosine that are going to be the zeros of the denominator. The range here is a little strange. It's going to be everything less than or equal to -1, or everything greater than or equal to 1, depending on which of these pieces I'm on. We have a cotangent function that looks a lot like the tangent function. They didn't draw it here, but it's going to go the other way, but it's also going to be shifted so that its asymptotes are the zeros of sine, and its zeros are the zeros of cosine, and it's going to be a decreasing function instead of an increasing function. They didn't show that one here. We probably are not going to talk about inverse trig functions for a while, so I'm not going to talk about these right now. I'll come back to them when we get to them, but they are going to be important, that if we want to say what is the angle whose sine value is, and so we will ask that question this way. All right, let's come back to here. So I'm going to, again, just start back here at the beginning, because we needed to talk about the library of functions before we could talk about the answer to some of these terms and concepts here. So what happens when we try and change the inside? Well, we're changing the input value, and we're going to cause a horizontal shift to happen because the change is happening to x, the input value. When we have a change on the outside, where we say something like f of x, the parent graph, was equal to x squared, and we say g of x is equal to x squared plus 3. Now, this is the old y value plus 3, so it's adding or subtracting to y, so this is going to be a vertical shift. That's different than, say, where we had our horizontal shift here. If we said x plus 3 quantity squared, we've got to change the x value before we square it. That's a horizontal shift. So let's look at the function g of x is equal to 2 ln of x plus 4. This is going to be based off of the parent graph ln of x. The first thing that I need to do is follow my order of operations, is I'm going to multiply. Multiplication comes before addition. So I'm going to have to stretch the graph before I shift it. They're not actually asking me to do that. They're just asking me which one comes first. And f of x is equal to 2x minus 1 to the third power. What comes first? Order of operations again tells me to do this multiplication that's inside the parentheses before this subtraction inside the parentheses before this exponent that's on the outside. Now I'm going to tell you that I'm going to cheat in this problem. What I would do in this problem to actually graph it is I would factor 2 out. I would say that this is 2 times x minus 1/2 raised to the third, which is 2 to the third x minus 1/2 to the third. And as long as I can get that constant multiplier out of my elementary function this way, as long as it's not something like sine or cosine or tangent or secant or cosecant or cotangent that I can't do that with, I'm going to do this, because this tells me that I'm going to shift 1/2 to the right, and then I'm going to stretch it by a factor of 8, and that's way easier for me to do than for me to deal with a horizontal compression here. We'll talk about horizontal compressions when we have to, but that is a problem where I would try and not deal with the horizontal compression if I didn't have to. If I have h of t is equal to 3t plus 4, then the parent graph of this, f of t, was 3 to the t, and I have shifted that 4 to the left, because I would take t plus 4 and set it equal to 0. T equals -4. This here is my horizontal shift of 4 to the left. Now we're going to look at the graph of each function in 6 through 10. Number 6 asked me to graph f of x is equal to -x² plus 1. So we're going to start with the graph of x². It's going to have a transformation where it's going to reflect over the x-axis, and it is going to be shifted up 1. So we know that it's going to have its vertex here at 0, 1. That it's going to open down. So it's going to go to 1, 0. It's going to go over here to -1, 0. When I go 2 to the right, I'm going to go 4 down. So 1, 2, 3, 4. And 2 to the left, I'm also going to go 4 down. And it's going to look like this. I didn't have to actually calculate anything, nor did I have to really do any factoring or anything like that. I based all of my drawing off of the transformations of what was going on here with the reflection and the characteristic points of x² and the vertical shift of +1. So all of those things, I took my characteristic points, reflected the y value to make it the opposite y value, and then added 1 to them. So where this had been characteristic points here of 0, 0, 1, 1, -1, 1, I took the opposite y value and added 1. So opposite of 0 is still 0, plus 1 is 1. Opposite of -1 is -1, -1 plus 1 is 0. Opposite of 1 is -1 plus 1 is 0. And that's how I got this. Number 7, it's a piecewise defined function. F of x is equal to 2x plus 8 for x less than or equal to -1, and -x plus 7 for x greater than 1. So we've got at -1, I'm going to stick it in to here, and this is going to be -2 plus 8 is 6. Got a slope of 2 as I go to the left. So I'm actually going to go down 2, left 1. Instead of going up 2, right 1, I'm going to go down 2, left 1. And that's going to give me my piece of the graph that goes to the left. And it's going to go through -4, 0 over here. It's going to have the point -1, 6 up here. Now I'm also going to stick in -1 to this piece. And I'm going to get 8, but it's going to be a hole. So 6, 7, 8, there's going to be a hole up here at -1, 8. And it's got a slope of -1. So I'm going to go down 1, right 1. That's going to get me to 0, 7. I'm going to draw my graph with a slope of -1. And it's going to cross the x-axis over here at 7, 0. So that's my graph. And some of my important points. There's nothing characteristic about that, though. There's nothing that's based off of a parent graph. I'm just being asked each piece as its own is based off of its own parent graph, though that was made up of 2 linear pieces that didn't touch one another. Number 8, f of x is going to be equal to a -x² for x less than 0, and x minus 1 quantity squared for x's between 0 and 3. 3 is not included, 0 is included. So 0 squared is 0. Come to the left, 1 squared is 1 times a -1. 2 squared is 4. It's going to be negative. We're going to be coming to, we're going to be taking this left-hand side of this parabola over here. It's a parabola that opens down that would have its vertex at 0, 0, but that's not included. Now I'm going to shift to the right one over here. Let's first stick in 0. It's 0 minus 1 is -1, -1 squared is 1. So we get this. Now our vertex is going to be at x equals 1 here. The x equals 1, this is 0. At x equals 2, this is 1 again. And then at x equals 3, this is 2 squared is 4. So 1, 2, 3, 4. And we're going to stop there. 3 is not included, so this is an open circle up here. 0 is included, it's a closed circle, so I'm coming down to my vertex and then opening back up like this in a piece that looks quadratic. Right? Number 9. Ask me for e to the x plus 1. So this is going to be an exponential. The horizontal asymptote is going to shift up 1 with the graph. So it's no longer at y equals 0, it's at y equals 1. When we are 1 above the asymptote, it's going to be at, when x equals 0, e to the 0 power is 1, 1 plus 1 is 2. So we're at 0, 2. This is an exponential growth function. It's coming like so. And this is the fastest growing function that you know of. The log function is the slowest growing function that you know of. If you get asked about whether it's growing faster or slower, something like that. Now we want f of x is equal to sine of x for all x's that are less than pi, and cosine of x for all x's that are greater than pi, and we're not going to include a value for pi. It's going to be an open circle there. So and So remember, our outputs are going to stay between -1 and 1 for both functions. For x is less than pi. So pi is, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi, so on. So I want the sine graph for pi or less. So that's going to be sine of pi is going to be 0. That's going to be an open circle there. And our sine value is going to be positive here. Coming up to 1. Pi over 2. Pi over 2, 1. Coming back down to 0. And then we've got just the regular sine graph over here. And it keeps going that way forever. So we've got that pattern continuing. At pi, our cosine of pi is -1. So we're going to come down here now. And then our cosine of 3 pi over 2 is 0. The cosine of 2 pi is 1. And we're going to follow the cosine graph at this point. We keep going like so. All right. Number 11 asks me the result of shifting the graph up 3 and left 2. So g of x is going to be x squared. We want that to be shifted up 3 and left 2. Well, we need to do the left 2 first, and then the up 3 is going to be x plus 2 squared plus 3, because horizontal gets taken care of before vertical, like that, and that's going to be the new function. Any even degree polynomial that is positive, it wants us to graph this. All right, so we want the vertex at -2, 3, and it's going to open up. So when I go 1 to the right, I go 1 up. When I go 1 to the left, I also go 1 up, based off the parent graph of y is equal to x squared. And there it is. It has the same shape as x squared. It's just been moved. Any even degree polynomial that is positive for x's between -2 and 4. So let's just say y equals x squared, and it doesn't tell us to shift anything. So it just wants us to graph one that's restricted. -2 squared is 4. 0 squared is 0. -1 squared is 1. 1 squared is 2. 2 squared is 4. 3 squared is 5, 6, 7, 8, 9. And 4 squared is 11, 12, 13, 14, 15, 16. It's way up here. And we've got graph. They want you to see some of the symmetry that's here, is what they want you to see. I didn't do a great job at getting the y-axis to scale. So But you should be able to see that these points, I tried to draw them equidistant off of the y-axis, but where I didn't have a piece over here to be equidistant, I got off a little bit here. Okay, result of shifting f of theta equals -2 theta plus 3. When I shift it down 2 and right 5. So when we shift it right 5 and down 2, this is -2 theta minus 5. And then we're going to shift it down 2. So this is going to be +1 then. So this is -2 theta plus 10 plus 1. And so this is going to be -2 theta plus 11. I think that's right. So we start off with, let's see here. We have y equals -2x plus 3, basically. So 1, 2, 3, going down to right 1, like so. We want to move this whole graph down to and right 5. So this becomes 5, 1. And that's right. And then this point here is gonna, that was at 1, 1. I'm gonna move it down 2 and right 5. So this is going to be at 6, -1. This is going to be a parallel line, has the same slope, and put in 6 there. I do get -1. That's correct. So I want another line with the same slope of -2. It's just going to change its y-intercept, and it's going to go through up here at the y-intercept is going to be 11. Piecewise defined function consists of t squared shifted down 1 unit for t is less than or equal to -2. A line with a slope of 3 and a y-intercept of 3 for t greater than 2. And we want to graph that. There's -2. 4 minus 1 is 3. There's a closed circle there. We're going to the left. So 3 squared is 9. 9 minus 1 is 8. 5, 6, 7, 8. We're coming up over here. This way we're already past the vertex. So there we go. For t equals 2 on this part, 6 plus 3 is 9. Sorry, -2, that's -6 plus 3 is -3. There we go. And it has a slope of 3, so we're going to go up 3 and right 1. And then we also want to have the y-intercept of 3 here. So it's going to go like that to the right. Again, this is an open circle because it's not included. Problem number 15. It's going to ask us to draw the line with a slope of 2/3 that passes through the point 1f of 2, where f of x is equal to x squared minus 1. So f of 2 is going to be equal to 4 minus 1 is going to be 3. That makes this the point 1, 3. So we have a point and we have the slope. Y minus 3 is equal to m times the quantity x minus 1. Y minus 3 is equal to 2/3 x minus 2/3. Let's change these to thirds. Y minus 9/3 is equal to 2/3 x minus 2/3. We're going to add 9/3 to both sides. Y is equal to 2/3 x plus 7/3. We're going to graph that. 7/3 is 2 1/3. So it's right there. And we're going to go up 2/3, which is going to get us up there to 3, right 1. So we're at the point 1, 3. And there's our linear equation right there. Now we're going to look at number 16. Number 16 says b of x is equal to x to the 3rd plus 6x squared plus 12x plus 8. And we have not dealt with any parent graph that shows us what to do with that. We're going to have to graph it knowing what happens with the end behavior and finding the x-intercepts, because this is just a polynomial. So we've got a y-intercept of 8 that we can graph, and we can start to factor this if we would like. I think I'm going to try something though. I'm going to try x cubed plus 8 plus 6x squared plus 12x as my grouping. This is x plus 2 times x squared minus 2x plus 4. This is 6x times x plus 2. Has a common factor of x plus 2. This is x squared minus 2x plus 4 plus 6x. That's x plus 2 times x squared plus 4x plus 4. That's going to be x plus 2 squared. So I end up with x plus 2 cubed. So there we go. So this is going to be a cubic function that is going to be shifted 2 to the left. So we have 2 to the left is going to give us -2, 0. And we're at going through 8 there. We would have 1 to the right, 1 up. So I kind of made that grow a little too quickly there. Go 1 to the right, 1 up, 2 to the right, 8 up. Or I'm sorry, 2 to the right, yeah, 8 up. 2, 3, 4, 5, 6, 7, 8. 1 to the left, 1 down. 2 to the left, 8 down. 1, 2, 3, 4, 6, 7, 8 is way down here. So we should have something that looks like so, where this point of inflection right here is at -2, 0. All right. That one was kind of tricky because we had to get it in the form where it looked like a parent graph first. Y of t is equal to t squared minus 6t plus 9. So this is t minus 3 squared. That's going to shift it 3 to the right. It's going to be a parabola that opens up. 1, 1, 2, 1, 2, 3, 4. Symmetry over here as well. And we're opening up and to the right and up and to the left. And I don't have the point up here, but 0, 9 is going to have to be up here as my y-intercept when I get all the way over there. So there's that one. Number 18. It says f of x is equal to x squared plus 4x plus 4. Just dealt with that hidden inside of number 16. This one was x plus 2 quantity squared. So we're going to shift 2 to the left, go up 1 and right 1, left 1 and up 1, right 2 and up 4, left 2 and up 4, and there we go. These are just sketches. You're going to get better graphs on your calculator. When you use your calculator, this is just conceptual right now. For each of the following here, f of x is equal to x squared minus 3x, and then call that I forget what that is. I think that that's mu of theta is equal to cosine of theta. And then g of w is equal to 3 to the w minus w to the third. Like that. They want us to, I'm going to call this parts A, B, and C. For 19a, we're going to shift each one up by 3. So we get x squared minus 3x plus 3, cosine of theta plus 3, 3 to the w minus w cubed plus 3. 20 asks us to shift everything to the right 2 units. So part A is going to be x minus 2 squared. It's 3 times x minus 2 is going to be x squared minus 4x plus 4 minus 3x plus 6, x squared minus 7x plus 10. B is, again, to the right 2 units, cosine of theta minus 2, and to the right, the cosine, or 3 to the w minus 2 minus w minus 2 to the third. If you want to, that's going to be 1/9 of 3 to the w minus w to the third minus 2 w squared plus 4 w minus 8. This is times 3 and times 3, so that's times 3 is 6 and times 3 is 12. So let me get my pixel eraser here. I used Pascal's triangle to figure that out. So minus 6w squared plus 12w minus 8. Okay. There's no like terms to add there, so we'd have 3 to the w divided by 9 minus w cubed plus 6w squared minus 12w plus 8 after we did the subtraction. Now we want to shift down 2 and left 1. So left 1 down 2. X squared minus x. 1 minus 3 is negative 2, minus 2 is negative 4. Cosine down 2, left 1. And I'm not going to get fancy with this one. Left 1. Down 2. I'm going to leave it like that. Now for number 22, I want to ask us to shift down pi units and right e units. So x minus e squared, x minus e down pi. Down pi and cosine theta minus e. C is going to be down pi, e to the right, 3 to the w minus e, minus w minus e raised to the third. Don't like the word flip here. It's not a mathematical word. I would use the word reflect, but let's reflect across the x-axis. To do that, we're going to change the sign of y. So we're going to multiply everything by -1. So this is going to be a negative x squared plus 3x. This is going to be a negative cosine of theta. And this is going to be a negative 3 to the w plus w cubed. 24, we want to reflect across the y-axis. So we're going to replace x with negative x. So that's going to be a negative x squared minus 3 times negative x. It's going to give us x squared plus 3x. Cosine of negative theta, since cosine is an even function, that's going to come back to be cosine of theta. And 3 to the negative w minus negative w to the third. So this is going to be 3 to the negative w. And then negative w to the third is the opposite of w to the third. So this is a negative times a negative is a positive, w to the third. Now we're going to look at the graph for number 25 and 26. 26 is on the next page there. Based on the shape of the graph below, could f of x be a polynomial? It could be. Yes, it absolutely could be. It could be cubic, or it could be, oh, could it be an even polynomial? No. No, it can't be. It has to be an odd power because the ends are doing opposite things. So opposite end behavior is going to be an odd polynomial. So B, yes, it could be. Could it be an exponential function? No, can't be, because it doesn't have horizontal asymptote that it's approaching on one side, right? We would need a graph that would be always increasing or always decreasing and approaching 0 on one end. Could it be a trig function? Theoretically, it could be, though it doesn't appear to be, because it doesn't appear to be cyclical. I'm going to say no, because it looks like this is going up forever and this is going down forever. It doesn't appear that they're showing multiple cycles that are staying at the same height. This is going higher than the highest point here. This is going lower than the lowest point there. So I'm going to say no, that it appears to be unbounded. Appears to be unbounded. And not related to tangent, secant, or cosecant. That would be unbounded reciprocal functions, cotangent. So it's theoretically possible, but I don't think so. Okay. Based on the shape of graph of g of x shown below, where did g of x go? There it is. So there's the graph. Could it be an even polynomial? Nope. This is exponential. This is clearly exponential. It's not an odd polynomial. Could it be exponential? Yes. It's going to be exponential decay. Could it be a trig function? No. So you're going to need to get to where you can look at graphs and say, I look at it and I see what the shape of it is. This one looks cubic. This one looks exponential. You have to just look at things and say, I recognize what the parent is of that child. And you're going to be able to figure out the transformations from the graph and be able to write the function from there. Okay, that's it. See you next time for when we talk about completing the square, one of my favorite things in algebra, and it's a very important skill in pre-calculus.